Section 1, Introduction, Unlocking the Secrets of Change. Calculus is a powerful branch of mathematics. It allows us to understand and model change. It is a fundamental tool in science, engineering, economics, and many other fields. Calculus helps us analyze motion, growth, and patterns in the world around us. It provides tools to study continuous change and its consequences. Calculus is like a lens. It helps us see the world in a new way. With calculus, we can study instantaneous rates of change, such as the speed of a moving object at a specific moment in time. We can also calculate the accumulated effect of change over time, such as the total distance traveled by a moving object. Imagine trying to find the area of an irregular shape. This would be a difficult task using traditional geometry. However, calculus provides us with tools like integration to solve this problem easily. By dividing the shape into infinitely small pieces, we can calculate the area of each piece and then sum them up to find the total area. Calculus is a testament to the power of human thought. It is a tool that has revolutionized our understanding of the universe. In the following sections, we will delve deeper into the world of calculus. We will explore its history, its key concepts, and its vast applications in various fields. Section 2, the two pillars of calculus, differentiation and integration. Calculus is built on two fundamental operations, differentiation and integration. These two operations are like two sides of the same coin. They are intricately linked and complement each other. Differentiation deals with instantaneous rates of change. It is like finding the slope of a curve at a specific point. For example, if we have a graph representing the distance traveled by a car over time, the derivative of this graph at any point in time would give us the car's speed at that exact moment. Differentiation helps us analyze how quantities change over very small intervals. It is used in physics to calculate velocity and acceleration, in economics to study marginal cost and revenue, and in many other fields. Integration, on the other hand, deals with accumulation. It is like finding the area under a curve. Going back to our car example, if we integrate the car's speed over a period of time, we would get the total distance traveled by the car during that time. Integration is also used to calculate volumes, work, and other important quantities in physics and engineering. These two operations are inversely related. This means that if we differentiate a function and then integrate the result, we get back the original function up to a constant. This fundamental theorem of calculus forms the backbone of calculus and connects its two main branches. Section 3, Ancient Roots, Glimmers of Calculus in Early Civilizations. While calculus is often attributed to Newton and Leibniz, its roots can be traced back to ancient civilizations. These early mathematicians and philosophers grappled with problems that required them to think about change and motion in new ways. Their insights laid the groundwork for the development of calculus centuries later. Ancient Egyptians, for instance, developed methods for calculating the volume of pyramids and other geometric shapes. These methods involve dividing the shapes into smaller units and summing up their volumes, a concept that foreshadows integration. The ancient Greeks made significant contributions to geometry and the concept of infinity, both of which are crucial to calculus. Eudoxus of Cnidus developed the method of exhaustion, a technique for finding the area of a shape by approximating it with polygons. This method is considered a precursor to integral calculus. In India, mathematicians developed sophisticated methods for calculating astronomical distances and predicting eclipses. These methods involved using trigonometry and infinite series, concepts that would later be incorporated into calculus. These early explorations demonstrate that the seeds of calculus were sown long before the 17th century. These ancient civilizations may not have had the formal language and notation of calculus, but their ingenious approaches to solving problems involving change and motion paved the way for the development of this powerful tool. Section 4, a mathematical renaissance setting the stage for calculus. The European Renaissance in the 14th to 16th centuries witnessed a resurgence of interest in classical mathematics and a spirit of scientific inquiry. This period saw significant advancements in algebra, geometry, and the understanding of functions, laying the groundwork for the development of calculus in the 17th century. Mathematicians like François Viète made significant contributions to algebra, developing a system for using letters to represent unknown quantities. This innovation allowed mathematicians to express mathematical relationships more generally and paved the way for the development of analytical geometry. René Descartes and Pierre de Fermat independently developed analytical geometry, a powerful tool that uses algebraic equations to represent geometric shapes. This innovation bridged the gap between algebra and geometry, providing a new language for describing curves and surfaces. The development of a more rigorous understanding of functions was another crucial step towards calculus. Mathematicians began to explore the relationship between variables and how they change with respect to each other. They developed concepts like limits and continuity, which are fundamental to calculus. These developments, along with the invention of new mathematical notations in the printing press, created a fertile ground for the emergence of calculus in the 17th century. The stage was set for a revolution in mathematics, one that would transform our understanding of the universe. Section 5. Newton and Leibniz, the architects of calculus. The 17th century witnessed the culmination of centuries of mathematical thought with the independent development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. These two intellectual giants, separated by geography and temperament, revolutionized mathematics and science with their groundbreaking work. Isaac Newton, an English physicist, mathematician and astronomer, developed his version of calculus in the mid-1660s. He called it the method of fluxions. Newton's work was primarily motivated by his study of physics, particularly his laws of motion and gravitation. He used calculus to describe the motion of objects and the forces acting upon them. Gottfried Wilhelm Leibniz, a German mathematician and philosopher, independently developed his version of calculus around the same time. Leibniz focused on finding areas under curves and developed the notation we still use today, including the integral sign and the derivative notation. While Newton and Leibniz made significant contributions to calculus independently, their work sparked a bitter priority dispute. Both mathematicians and their supporters engaged in a prolonged and acrimonious debate over who deserved credit for the invention of calculus. Section 6. The Calculus Revolution, from Theory to Application. The development of calculus by Newton and Leibniz marked a turning point in the history of mathematics. Calculus quickly spread throughout Europe, sparking a revolution in scientific thought and leading to countless advancements in various fields. One of the first major applications of calculus was in astronomy. Newton's law of universal gravitation, formulated using calculus, explained the motion of planets and celestial bodies. Astronomers could now predict the positions of planets with unprecedented accuracy. Calculus also revolutionized physics. Scientists could now describe the motion of objects with variable acceleration, leading to breakthroughs in understanding concepts like force, momentum, and energy. The applications of calculus extended far beyond physics and astronomy. Engineers used calculus to design bridges, buildings, and other structures. Economists used it to model economic growth and analyze market behavior. The spread of calculus was facilitated by the development of new mathematical journals and the establishment of scientific societies. These platforms allowed mathematicians to share their ideas and collaborate on solving problems. The development of calculus was a truly international effort, with mathematicians from across Europe contributing to its growth and refinement. Section 7. Calculus in Action, Real-World Applications. Calculus is not just an abstract mathematical theory, it is a powerful tool with countless applications in the real world. From predicting the spread of diseases to optimizing the performance of airplanes, calculus plays a vital role in shaping our understanding of the universe and improving our lives. In medicine, calculus is used to model the spread of infectious diseases, predict the effectiveness of treatments, and design medical imaging techniques. For example, epidemiologists use differential equations, a fundamental tool in calculus, to model how diseases spread through populations. In engineering, calculus is essential for designing bridges, buildings, airplanes, and other structures. Engineers use calculus to calculate stress, strain, and other factors that affect the stability and safety of structures. They also use calculus to optimize the design of airplanes. minimizing drag and maximizing fuel efficiency. Calculus is also used in finance to model investment growth, assess risk, and develop pricing models for financial instruments. Financial analysts use calculus to understand how interest rates and market fluctuations affect the value of investments. These are just a few examples of the countless applications of calculus in the real world. Calculus is a versatile tool that can be applied to a wide range of problems involving change, motion, and optimization. Section 8. Beyond the basics, exploring advanced concepts. While the fundamental concepts of differentiation and integration form the core of calculus, the field extends far beyond these basic operations. Advanced calculus explores more complex concepts and techniques, providing powerful tools for solving even more challenging problems. Multivariable calculus extends the concepts of calculus to functions of several variables. This branch of calculus is essential for understanding phenomena that involve multiple variables such as fluid dynamics, electromagnetism, and thermodynamics. Differential equations, a fundamental tool in calculus, describe the relationship between a function and its derivatives. They are used to model a wide range of phenomena from population growth and radioactive decay to the motion of planets and the spread of heat. Vector calculus deals with vectors, quantities that have both magnitude and direction. It is used to study fields, which are regions of space where a certain quantity has a value at every point. Vector calculus is essential in physics and engineering for understanding concepts like fluid flow, electromagnetism, and gravitation. These advanced concepts in calculus provide a deeper understanding of the universe and enable us to solve complex problems in various fields. Section 9. Conclusion Calculus, a timeless legacy. Calculus, the mathematics of change, stands as one of the greatest intellectual achievements of humankind. From its ancient roots to its modern applications, calculus has revolutionized our understanding of the universe and continues to shape our world in countless ways. The development of calculus by Newton and Leibniz in the 17th century marked a turning point in the history of mathematics. Their groundbreaking work provided a powerful tool for understanding motion, change, and optimization, leading to breakthroughs in physics, astronomy, engineering, and countless other fields. Calculus is not merely a tool for scientists and mathematicians, it is a testament to the power of human thought and our ability to unravel the complexities of the natural world. Its elegant theorems and powerful techniques continue to inspire awe and wonder, reminding us of the beauty and order that underlie the seemingly chaotic universe. As we move further into the 21st century, calculus will continue to play a vital role in shaping our world. From developing new technologies to addressing global challenges like climate change and disease, calculus will remain an indispensable tool for understanding and improving our world. The legacy of calculus is a timeless one, a testament to the enduring power of human ingenuity and our insatiable curiosity to comprehend the universe we inhabit.